Hello, my name is George Kantor. I'm from the Robotics Institute at Carnegie Mellon University, and I'm here to talk today about some work we've been doing in our group about using semantics to help with SLAM in natural environments. And specifically, we'll talk about past work we've done in agriculture and looking forward to future work we're planning to do in forestry as part of the Safe Forest Project. So the talk is going to have three basic components. We'll give some background on what I would call standard SLAM approaches, sort of the standard visual inertial LIDAR, point cloud building kinds of SLAM that lots of different people have used in lots of different settings. Talk about a specific implementation we've come up with in my lab, and its strengths and its weaknesses. And then, one of the weaknesses is that it doesn't perform as well in natural environments as it does in built man-made environments where there are sharp corners and flat walls and things like that. So that'll lead into the semantic segmentation part of the talk. So, with deep neural nets these days, there are a lot of really powerful tools to do semantic segmentation in natural scenes. We've developed a lot of these from the application side because we want to do things like count grapes or measure how high a plant is. But we'll talk about what we've done there. And then that semantic segmentation can be fed into the mapping process and actually improve the mapping process. And then finally, once you have all those things together, we can consider the geometry from the SLAM, the semantics from the semantic segmentation, and you can build up a topology of how the different semantic components are connected. And that gives you an understanding of how a plant is constructed, which is important for a lot of different applications. But if you want to understand the plant, understanding its structure is very important. So I'll just give a brief overview of this method called VIL-SLAM, Visual Inertial LIDAR, Simultaneous Localization and Mapping. This is a method developed in my group. We have this relatively straightforward payload that has a Velodyne LIDAR on it, has a suite of cameras on it. There's a little IMU here, this little orange box here, computer on board. So we can take this thing and move it through an environment, and in real time, we can build up maps, 3D maps. The most common form is a point cloud map of the world, and there are a whole bunch of different parts of this. Now, as many of you know, SLAM is a very active area of research and has been for some time. So there are lots of powerful tools here. I'm going to present our implementation, but it's really not that much different from dozens of other implementations that are out there and do similar things. So here's just kind of a snapshot of it in action. This green line is kind of that package being moved through a workspace. You can see as it moves around, we're incrementally building up this point cloud model of the environment that we're looking in. This is obviously an indoor environment. And if you look closely and you understand how to look at these point clouds, you can actually resolve some pretty small features. There's some nice edges. You can see the walls of rooms. You can see objects of the clutter on the floor and things like that. So, nice method. We'd like to be able to do this kind of thing in natural environments as well, to be able to apply it to forestry. And that's kind of what we're working towards here. We've applied this in lots of different settings. The one you just saw the video of was this is our lab at Carnegie Mellon, and you can see it's kind of messy and there's lots of little small pieces on the floor and stuff like that. But that's basically how it works. We get this high resolution 3D model, works great in the lab, works great in hallways, works great outdoors when there's scenes with buildings in them. Works great. It actually does a pretty good job on the trees here. When there's buildings in the scene as well. So would really like to bring that kind of power into understanding 3D scenes in forests. And to understand the work we need to do to get there, I want to dig just a little bit into this pipeline. There's a lot going on here. There are over a dozen different components all kind of working together to generate these maps. But there's one theme that comes up over and over again. And that is this notion of feature matching. So you see it here on the front end where we're trying to estimate how the cameras are moving. And the way we do that is by finding features in the camera, looking at where they are in the camera image over successive frames and doing some math to back out how the camera must have moved. Again, there's a feature that is used as part of the global loop closure. So if you go far away and return to a place, there are visual features that we can use to realize that we came back there. You know, there's some features being used to match the stereo pairs. There's some LIDAR scan matching that goes on, and the approach we use doesn't just match the entire cloud. It actually pulls out some features out of the LIDAR scan and matches those, because that's a more efficient way of doing it. So this idea of feature matching comes up over and over again. There are dozens of different features that have been proposed, many for computer vision, also many for LIDAR point clouds. So, you know, you can go through literature and you can find those and you can use them. And in most cases, you can be very successful. If you dig into the guts of these feature matching things, you know, you see these kinds of you'll see this kind of picture a lot, right? On the left here, this is an image of a scene. On the right here, this is an image of a scene, you know, in the next camera instance, so a little bit later. And these yellow lines are showing the feature matches, right? So every little feature that was seen in the image on the left is matched to its partner feature in the image on the right. And when this feature matching is working, what happens is you see all these nice parallel lines, right? Because, you know, this feature is actually appropriately matched to this feature over here. And there's a feature down here and it's appropriately matched to this feature here. And so when this works, it's great. And this is what it looks like. But getting to the challenge of what we're trying to solve here, we want to look at natural environments. All right, so this is a scene from a sorghum field. So sorghum is a plant. It's you know, it's grown all over the world. It's one of the oldest cultivated crops. There's 40,000 different varieties of it. A common variety is grain sorghum. So, you know, I kind of think of it, it looks kind of like wheat on steroids, or corn with a big head on top of it. So this is the sorghum panicle, and these are seeds. This is grain, okay? And so this particular sorghum, this is going to become probably pig feed if you're in the United States, although there are some health food products that use it. It's high protein, gluten-free grain, so people like this kind of thing. Anyway, that's some context you don't really need, but I want to go into this sorghum field and I want to measure things about these panicles. And what I really like to do is build up a 3D model of what's going on here, so I can assess things like the volume of the panicles and the size of the seeds and things like that. And if I use the standard features to try to do the matching that's fundamental to the mapping approach, I have problems. So you can see, remember how I said, you know, in the last slide, if the feature matching works, you get all these nice parallel lines that get you from one frame to the next. Here, this is the SIFT feature, which is one of the standard computer vision features. And you can see the feature association from the left image to the right image is not working at all, right? These lines are this crisscross mess. If I try to feed this into my mapping algorithm, things are not going to go well. It's just going to fail. And so we've got to find a way in natural scenes to do this sort of feature matching. Now, why am I in the sorghum field? I'm in the sorghum field. One of the reasons is because we want to count seeds. So let's just take a little sidetrack here. We have neural networks these days, and we can do supervised learning, lots of powerful supervised learning tools. And so when I want to count seeds, I can look at a bunch of images, I get them manually labeled, I train up a neural network. In this case, we're using a Mask RCNN, and I can do seed detection. So there's little green dots where all the seeds are here. And so I need to do this anyway for the application. The main reason we're taking these pictures is so we can count the seeds. So we need to do seed detection anyway. But the thought that came to us is, you know, these seeds also make really good features. First of all, they're there because we know they're there because we're counting seeds. That's the whole point. They're also sort of very well defined. They come in clusters. They're going to maintain sort of similar appearance from viewpoint to viewpoint. And these are all the properties of good features. So let's try to use these seeds as a feature matching thing. You know, without going into too many of the details, this actually works pretty well. So here you see, you know, this was the original SIFT match feature where you're having all these mismatches. Here's a method that we've come up with to match based on seeds and on little graphs of the seeds locally. And you see we get back to this lots of parallel lines, good feature matching for a SLAM pipeline. So that's, this is sort of the high level take home message of this talk, is that we need to do semantics in these scenes a lot of times anyway, and we might as well use them for mapping, and that has a whole lot of advantages associated with it. Okay, so let me dig into the details of a couple of examples where we've used this technique, and we'll sort of get into exactly what's going on and what it takes. What you'll see here is that in order to do this, as of yet, we don't really need to invent any new fundamental science. There are lots and lots of different tools out there for doing things like extracting features and registering features and building 3D models. And so what we can do is we can take those and add in this little bit of information about the environment and build up these pipelines that can get the kind of capability we want in these more natural environments. So one of the places we got started here was in imaging in vineyards. Okay, so this is a custom camera unit. It's really nothing that special. High resolution stereo pair, synchronized flash lights, right? So these are xenon flashes, synchronized so that when they're on, they're like 10 times brighter than the sun. They're only on for a very, very short period of time. The cameras are synchronized with that lighting, and so basically we drown out any ambient light with this approach. The other advantage is then the shutters can be open for a very narrow time, which means that we don't get motion blur. So this thing can be driving along. Here you see it sort of strapped to the back of an ATV vehicle. Can be driving through the field, bouncing around, and we get good, consistent images, regardless of the ambient lighting conditions, regardless of the fact that we're bouncing around. Just to give you sort of an idea of what this looks like in practice, here's the camera hanging off the back of an ATV. In this case, we actually have the leaf blower on it. It's there to sort of move some of the leaves out of the way, because what we're really doing is looking at these grapes. Over here on the right, you can see the image that comes out of the camera, right? So we're driving down the row, we're taking all these pictures. This is just the sequence of images that come out. The main task in this case is counting grapes. And so we'd really like to be able to model in 3 dimensions what we're looking at, so we can better reason about how to count the grapes that are there. So the kinds of semantic extraction processing that we do for the application are pretty simple things, right? One thing we do is we just detect the grapes. Where are they and how big are they? Another thing that we do is we grade individual grapes based on their color. So this is sort of a ripeness measurement. We also cluster grapes into clusters and grade the whole cluster, right? So right away, you can see 3 features, right? We've got the grapes themselves. We've got the grade of the grapes, which is sort of a descriptor on that feature. And then we've got these clusters sort of lumped together, which is yet another feature. So if you're thinking about this from the mapping perspective, it's a relatively straightforward thing to put 2 and 2 together and get some sort of semantic mapping pipeline. Another thing we've done is, again, driven by the application, is we've developed some tools to match grapes from one frame to the next. Now, this is not what I'm showing here in these images. This is not really a mapping problem, but it's more of a feature association problem. So what we have on the left is an image from a grapevine one day, and what we have on the right is an image from the same section of the grapevine taken a few days later. And so we're associating individual grapes on one side to their partner grapes on the other side. So again, you see the lines are nice and parallel, which is like what we like to see when we have good feature matching. The reason we're doing this is not mapping. The reason we're doing this is because we want to track the color of these grapes, and the growers and the viticulturists who work with this data like to see how color progresses over time. So this gives them a way of measuring that. But as an engineer, as someone who builds maps and models, you recognize right away that this approach, this ability to match grapes from frame to frame, it will be also useful for the mapping. Okay. So we've put together this grape mapping pipeline, which, now that you've sort of heard the high level bit, most of you could put these pieces together by yourself, right? So, because I think it's a pretty straightforward approach. We start off with a stereo image pair. From that pair, we get a 3D model of the scene. We also do semantic segmentation and get a semantic model of the scene. We merge those two together to get a 3D model of the scene that has both semantics and the 3D geometry. We do some shape primitive fitting. Grapes happen to look like spheres, so we sort of take the different instances from this segment, we fit spheres to them, and now I've got this nice, clean, lightweight shape primitive that I can feed into my different SLAM techniques and use to build a model. Okay, so let's walk through this kind of in gory detail here. The dense stereo reconstruction, we're using semi-global matching to get a dense stereo field. This is a case where you really need to have dense stereo, and this works pretty well. So there's, standard tool off the shelf, take a stereo image, works pretty well in this environment, let's use it. Now we tried out, lots of different ways of doing this. This one turned out to be the best. Instant segmentation. So, for instant segmentation, we're using Mask RCNN. Mask RCNN, pretty standard now. It's become it's a very powerful tool. Lots of people are using it for lots of different things. We use it to look at these images of grapes and to segment them out into individual instances of grapes. And so, what we do is we take this image from the camera, we break it up into a bunch of small images of the, sub-images of the appropriate size. We feed that into the network. We get this mask that has all of the different instances of grapes segmented out as pixels in the image. And then we reintegrate that back into one image where we can basically see all the grapes. So this is very useful for seeing grapes, sizing grapes, etc. We're using it here in a mapping pipeline. Right. The next step is now I've got these two things, and I want to pull them together into a single thing. Right. I've got the depth map, or my 3D model of the current scene. I've got my semantic labels, where all the grapes are, how much area they take up in the image, and I want to pull those together into a common product. And the way we do that is pretty straightforward, right? I have the depth map. From the depth map, I can generate a point cloud. Point cloud has all the points in 3D space. I have my image mask with my segmentations on it. I can just project those segmentations onto the point cloud. So this is a simple projection operation. And what I wind up with is a 3D point cloud. It's dense, right? Because I use dense stereo to get it. So it's a high resolution 3D point cloud. And the different grapes in this point cloud have, they have their instance labels associated with them. So if you think about this, if I took this point cloud and I hadn't labeled the individual grapes, the point cloud is really pretty messy, right? It would be almost impossible for you as a human to segment out individual grapes in the raw point cloud. But since I'm segmenting them in 2D, projecting that onto the 3D model, now in the 3D model, even though the point cloud is kind of messy and it's incomplete, there's shadowing and things like that, I can still see now that this is made up of a bunch of grapes, and that's the idea here. Okay, so the next thing is I've got this 3D point cloud model. I need something lightweight to use as a feature. This is where a little bit of sort of human intuition, feature engineering comes in. We recognize that grapes are mostly spherical, so we attempt to use spheres. Now you could use ellipses as well. That's probably a good next step, but we've done spheres. The basic idea is pretty straightforward. We use MLESAC, which is like a variant of RANSAC, for each instant in this cluster of point clouds, right? So I'll segment out all these orange dots here. I'll feed them into MLESAC, and MLESAC will search for the center and radius of the sphere that best fits those points. And I just loop through all my instances and I do that over and over again. And so as a result, I go from this kind of messy reality down to this very clean, representation of what's going on in the environment. Now, you lose some information here, of course, but there are advantages in that now I've sort of got discrete symbolic representations of all of the grapes, and I also have representations of their geometries. Okay, and so last but not least is I've got these features. I can put them into a SLAM pipeline. Now, there's lots of different ways I can do this. There's lots of different techniques in SLAM. One of the underlying points of this talk is that improving the features and improving the feature association will improve lots of different SLAM pipelines. But the basic idea is pretty straightforward. Here I am. This is maybe a part of a grape cluster I've seen at one time. This is a part of the same grape cluster I've seen at the next time. And so I can do my association between these spheres now, right? Which are relative. This becomes a relatively simple geometric mathematical analysis to do to match these spheres up. Line them up, and then once I have the relative transformations of the spheres, I can merge these two scenes together into one combined model. And I also can estimate how the camera must have moved to get from the one scene to the next. Right? So this is one of the elements of SLAM, right? The combined model, being able to take all these features, register them together in a 3D space, and the incremental motion of the camera. And these pop up in SLAM pipelines all over the place. So whether you use this as part of a traditional EKF SLAM where the grapes are features, or whether you use these as edges in a factor graph and do factor graph SLAM, whether you use them as sort of raw points and do kind of ICP but with grapes instead of laser points, you can do all those different things, and the grapes just help you do it. All right, so let's look at how this actually works. Hopefully the video comes across in high enough resolution that you can see. This is sort of a scene that's kind of 3 or 4 successive images with our stereo camera pasted together and then modeled using the technique I've shown before. And I'll just sort of start it. We're kind of looking around at it. And the thing to look at is that, the grapes are the objects that we modeled geometrically. And so when we kind of zoom in here, there's a little bit of video compression artifact, but the grapes themselves are resolved really well in this model. And the reason they're resolved so well is because we did this, semantic segmentation geometric primitives, right? If you look at the rest of the point cloud, the rest of the point cloud didn't resolve as well because it's using sort of non-semantic methods to match the points together. So, future steps obviously involve segmenting out branches and leaves and things like that, and matching them as well. If we do this over a longer scale, this is now a section of a grapevine that is several meters long. And on the top, we've just basically run our SLAM algorithm. The green line is the ground truth trajectory of the camera as it moved down the row. The red squares represent the camera positions at each point in time as we move down the row as estimated by the SLAM algorithm. And this kind of mess, it's hard to interpret, but this is kind of the point cloud, the 3D model of that section of the row that we have built up. So if we do SLAM with our pipeline using the grapes as these geometric primitive features, we get a nice reconstruction. The camera doesn't drift away from its actual trajectory, and we get a pretty good reconstruction of the row. If we use a standard method, like if we just use ICP, making our best bet to use all the kind of modern methods, using ICP to do scan registration, what we find is that, we can still build a model. It's a little bit noisier, but, over this section of a few meters, the camera poses and the model itself, they drift significantly. So we'd really like to be able to use these techniques to model tens or hundreds of meters of rows. And so this level of drift is going to become completely unmanageable after a while. So if we do this geometric segmentation, we get improvement. Okay, let's look at another example. Okay, so this is still grapevines. Now, instead of looking at them during the summer when there's grapes on the vine, we're going to look at them in the winter when all the leaves have fallen off. And there's a few different operations that growers have to do that time of year. But we put together this platform that has two, these two things here are stereo cameras, a lot like that big red box I showed earlier. Now we're using two of them. They're in a different package, but they're basically the same thing. We have LED flashes here instead of the xenon flashes, and there are the same kind of high resolution stereo pair in the middle there. And this thing's on a slider, so we take it out in the we pull up to the vine, we slide the thing, and then we can build up a 3D model of what's going on. These are what the kinds of scenes look like. They look all different. They're generally these kinds of tangles of branches and just kind of messy. It's nice because the leaves are gone, so there's not a lot of occlusion. But there's it's just kind of messy. So what we'd like to do is go through the field, build models of these things, and start to understand their structure. One of the tasks that would be nice to automate is pruning during this dormant season. And in order to prune, you need to be able to understand the structure of the vine, and you need to be able to understand where features, in particular buds, are on the vine. So let me give a little more detail about that, right? So this is a grapevine. This is the cordon, which is the sort of growth that grows over many years. And then, there's a trellis wire that goes across here that holds the grapevine up. And then these things that come off, this is the annual growth, right? The cane, they're called canes, these thin little whips that grow off of the cordon. And they're just 1 year's worth of growth. And at the end of the year, they're basically cut off, and then they grow new ones the next year. And then along the cane, there are buds, okay? And the buds are the sites along the cane where either leaves or grapes will come out or have come out when we're looking back in the past. So what I want to do is, in my modeling, is I want to understand not just the geometry of this. The geometry is tricky. I want to understand the geometry. I also want to understand what the parts of the plants are, how they're connected, and where they are. And so, this sort of image from left to right gives you an idea of what we're looking at here. So here's sort of a close-up of a bud, close-up of a bud, close-up of a bud. We can use deep learning techniques to identify, to locate the buds in these camera images. And then I can use those buds to do a 3D modeling to get a coherent point cloud over this entire vine. So we have a pipeline, in spirit, it's very similar to the Grape mapping pipeline. We're taking these building blocks that are well known from the literature, and we're pulling them together in different ways. And again, we're doing this trick where we take the stereo pair, do the dense stereo reconstruction, do the bud detection, right? Last time it was grapes, this time it's buds. We project the labels from the buds onto the dense stereo. And so now at this point, I have this kind of point cloud that has semantic labels on that. I do that from the top camera. I do it from the bottom camera. And then, I can register these two together to get sort of a single labeled point cloud. And then now I can do some geometrical analysis. In this particular case, we're using singular value decomposition. And the idea is that we look at sort of small segments of the point cloud. In particular, sections around buds, because buds are kind of the features that hold everything together here. And by doing SVD analysis, we look at that point cloud, we look at the eigenvectors associated with that collection of points, and we can tell whether the region is approximately spherical, approximately cylindrical, or approximately planar. And when we're looking at a scene like this, where these, we've got this tangle of sticks and vines, canes that we're looking at, I know that these things locally are approximately cylindrical. So that's how the SVD analysis helps us. Basically we sort of fit little cylindrical primitives onto the canes using SVD, and then we do a region growing approach. Again, if I fit a bunch of cylinders onto places of the canes, the cylinders have an orientation. You can imagine how you would sort of grow those cylinders out, connect them together into a model of the entire vine. So I have a graphic illustration video here of kind of how all that works. You can see we start with the output of the first stages, which are the 3D point cloud modeling, the bud detection, right? So the buds are in green here on this image. And then the projection of those buds onto the model, right? And these things help each other out. The buds help the model helps us place the buds. And from there, let's hit play here. So, we can look at this model. This is a nice 3D model, dense stereo. And so now I can do this cylinder matching and region growing approach to segment out the canes. And then once I have the canes segmented out, I can go from the cordon wire, which is kind of the center of the vine, and I can count the buds radially outward from that cordon wire. So what I have here now is a model of my vine that includes the geometry, right? I've got a point cloud. It includes some semantics. I've labeled buds and I've labeled canes. It also includes some topology, right? I know which canes are connected to which. I know the orders of the different buds along the cane. And so, in addition to just it being nice that we have more knowledge about this vine, we can address the problem we want to solve, which is dormant season grapevine pruning. So, if you are a grape grower, at the end of the year, your recipe is to leave a certain number of buds on each cane. So now with this modeling approach, you can imagine going down the row, building the model, building up this representation we have here, counting the buds, and then from there you can pick a cut point, right? So if my recipe is that I leave 1, 2, 3 buds on this cane, then I know that I need to make the cut right here. Of course, since this is a 3D model with geometry, I know the X, Y, Z position of this. And so if I've got a robot arm, I can go in and make the cut. And just, to remind you, this picture, this is our platform. And I didn't mention it the first time we looked through, but this is a robot arm with a cutter on the end of it. So once you've got this model, it's a relatively straightforward task to reach in and make that cut. All right. And I think this is just the beginning of kind of a long story that could be done here. So now that I have this model that contains the geometric and the semantic and the topological information about a plant, I can start to do even more interesting things. One of the things we care about, especially when we start thinking about using robotics to manipulate these kinds of structures, is we care about, the tree is a mechanical thing, and when I touch it, it's going to move, right? And it's going to push back on me, or it's going to flex out of the way, or it might break. There's lots of things that could happen. And so the model I built in the previous video, again, geometric, semantic, topological. The semantic part was basically a bunch of cylinders, and the topological part was how those cylinders are tied together. So if I've got a bunch of cylinders tied together, I can make some assumptions on the dynamics of the tree, like maybe those cylinders are rigid but held together with torsional springs. It's a fairly common flexible beam model. So I'm basically assuming that the parts of the plant are flexible beams, which, based on my experience with pushing on plants, that seems approximately right. And we can do things like make the spring constant be proportional to or inversely proportional to the diameter of the cylinder at a given point. So we're going to have sort of weak springs out here, very stiff springs up on the trunk. Lots of standard math is out there to figure out what the dynamics of these kinds of systems are. So we can do the math, we can come up with a dynamic model for this. There's lots of great finite element modeling tools and 3D rendering tools out there. So I can build this kind of model where now this is the vine I showed in the previous scene or something very similar to it. and I can simulate what's going to happen when I apply a force to it. So this is, to me, this is really exciting, because the holy grail here, the reason I'm spending all this time modeling plants is because ultimately we want to use robots to go in and do really intelligent manipulation actions on plants. And so we need this kind of modeling to understand what's going on. So now I've got a model, and you can think of this mechanical modeling as one more step at the end of my pipeline that we can use to simulate the dynamics of the plant and how it's going to interact with a robot when I start pushing on it. Okay, so that's great. Those are applications in agriculture. That's the past work. We've developed pretty much all this stuff for agriculture. Now, Carnegie Mellon, my team at CMU has gotten involved in the Safe Forest project. And so we're taking these ideas and we're moving them into forestry. And so what I'm going to talk about now is really future work. We haven't gotten very far down this pathway yet. But I think that many of the ideas that we develop will be extremely helpful in the forestry application. And in particular, one of the things we want to do in the Safe Forest project is to look at a scene that's got a lot of cluttered vegetation in it, figure out what vegetation is okay to have there, what vegetation needs to be removed, what vegetation can be removed. And so we need to do things like distinguish trees from sort of ground cover shrub kind of things. And we need to do things like figure out how far away the trees and the shrubs and the grasses are from the critical infrastructure of the power lines and so forth. And so if you think about the requirements from those perspectives, this idea of having a model that has both the geometry and the semantics and some topology seems like a really useful thing. So we basically want to take these ideas, apply them to the forestry application. Here's what we've done so far, and we're just getting started. So this is our VIL-SLAM mapping payload, and here you can see it's attached to a drone. Drone flies in this sort of forested area or just outside of the forested area. And the goal is to look at a scene like this and eventually be able to model what's going on here, right? There's these tree trunks, there's this kind of upper story canopy, there's this kind of lower story canopy, there's some grasses and shrubs along the ground. We want to do the best job we can of understanding what's going on in that scene. So here's where we are, and this is basically just taking VIL-SLAM, putting it on the UAV and running it. So we haven't started with the semantic side of things yet. But if you're not used to interpreting these scenes, what we're seeing here is this is kind of live on the VIL-SLAM. The colored stripes are the LIDAR, the instantaneous returns from the LIDAR, and the white points here are the 3D model points that are being built up. So you can see we start with nothing, and as the drone flies around, it starts to build up this 3D model. And as a smart human, there's some skill in learning how to interpret these scenes, but as a smart human, you can sort of start to tell that you can see the structure, right? Here are the tree trunks. Upper story canopy is kind of up in the top. Lower story canopy is kind of down in the bottom. There's flat ground. And so, this map it's okay. It's not great. I would like it to be cleaner. I would like to be able to do it at a larger scale. And I would like to have the kinds of semantic labels and topology that we've seen in our agriculture work. And that's exactly what we're going to do. So we'll take these ideas, we'll apply them to forestry. Would love to hear, looking forward to this workshop, and would really love to hear people who are more familiar with what the challenges are in forestry. Are these techniques useful? What kinds of specific measurements and models would you like to have about these scenes? Because to me, it's all about the application. We really want to just solve problems. Okay, so that's pretty much all I have to say. Just to give you the high-level overview one more time, right? The philosophy behind this message, and that's that we have these really powerful 3D modeling techniques, but they have one of their Achilles heels is the ability to do feature recognition and association. And so semantics can help out there. So semantics can strengthen the 3D modeling techniques. But this actually goes both ways, right? Once you have good 3D models, the 3D models can help strengthen the semantics. So we saw this like in the Grapevine pipeline where we have the 3D point cloud, and that we could take the 2D semantics, project them onto the 3D point cloud, and then generate that sphere model, which is a much more representative, compact semantic model of what's going on there. But it wouldn't be possible without the SLAM. So there's this back and forth between the SLAM and the semantics. I think there's a lot of work that can be done without doing really fundamental work in these areas, right? So the tools we're using, people worked hard on, right? There's a lot of different SLAM tools out there. There are a lot of different deep neural network architectures that can be used for semantic segmentation and instant segmentation and masking and those kinds of things. I don't think we really need to work on improving those tools. Other people will do that for sure. Those things will move forward. But at the level I'm working at, we can take these tools, we can put them together, we can use these ideas to get some interesting things done. And then last, the reason we're here talking in a forestry workshop is that these things are good and even necessary, I think, to bring this kind of modeling into natural environments, because of the fact that the feature extraction can be difficult in those environments, because of the fact that those scenes have so much clutter, so much occlusion, they're kind of densely filled with lots of different objects. We really need to have the semantic information to help us keep things straight. And the applications, the reason we're there, we always have to remember as engineers, if we're in an environment taking pictures and building models, it's because somebody wants that information for something. And so, the semantics really are the information they want. How many trees are there? How big are the trees? Where are the bushes? How close to the power line does the canopy come, and those kinds of things. All right, so that's it. Thank you for listening to me. Just a few minutes to sort of point out, what I've shown is the work of a whole bunch of people in my group. We have a really interesting collection of people with different skills, looking at this problem of perception and robotics in agriculture, in natural environments, now in forestry. Also, definitely the Safe Forest team. We're really happy to be a part of that team and move into this forestry domain, learn about these techniques, and hopefully learn about the challenges there and use some of our techniques to solve them. We have a lot of partners and a lot of sponsors. Looking back, we get a lot of support generally from the USDA, the National Science Foundation, ARPA-E, which is the Department of Energy, ARPA group. And also we do a lot of work with industry organizations and grapes and tree fruits. That's all I have to say. Thank you very much.